Okay, now we are ready. So last time we talked about steganography. We completed basically the overview, and the last thing we saw was that we talked about a tool how you can test yourself some patterns. That was this is it? Yeah, covert channel education analysis protocol. So you can also download it. It's on GitHub. Professor Steffen Wenzel, I think he's professor in Worms, had this nice tool, and basically there you can set up your own server and test various examples how you can take influence on the messages that are sent. And I think in the next lab exercise, this is also what we are going to test. And what you, for example, can do is to use HTTP version 1 or 1.1. That could be a hint to the recipient to signal something, or how you can, that's a mistake. No, why did it jump away? Here's an issue, because it's PowerPoint tries to modify this double minus to a long line. So yeah, basically you can also, so all of these smaller letter or small or large letters are transparent to the protocol, so it's equal, and there are no differences, but of course the recipient can make modifications. And we concluded with this small video on how the let's select this. Okay, so to once again have the video where we cannot see anything because it's too small, but we can you will experience it anyway in the lecture, in the lab, where you have this doesn't help, where you test out these various modification options. You run your own HTTP server, and then the HTTP server is reporting what kind of information it received, and in Wireshark it can then be logged what kind of behavior was observed, especially, let's say, the changes in HTTP 1 or 1.0. It's hard to see. And the other element that was changed in this example is the time by which the packets were sent out, especially that you can take influence on what inter-packet times you use, whether you use, let's say, 100 milliseconds or 300 milliseconds. But it's hard to see, I must admit. Maybe I need to make a new recording with larger font size. But what I wanted to show is, let's say this part, it's over here. And what should be observable, at least on the, so let's make it this way, that way. It's even worse. It's even worse. Okay, so basically the inter-packet times are also changing. So it's still a valid tool, and it's used, and there are different parties who are interested in steganography, and therefore it makes also it's reasonable to look into the options that can be used. And basically, if you have this kind of patterns, maybe it might make sense to look for them. If you are in control of the network, if you can supervise it, if you can monitor it, then to look for these patterns as well. Okay, so now we are starting with the next chapter. It's on malware. And basically we will look into what kinds of malware we have and how to detect it, and what kind of tools we have in order to address this issue. And let me just see, because I'm always a little bit paranoid about OBS, whether it's recording correctly. Yeah, okay. So, so just have the case study at first. What happened? So 20 years ago, at midnight, there was some simple UDP packet that was sent, and 1 hour later, large parts of the internet were no longer reachable. And we want to look into what happened. So what at that time happened? There was an SQL slammer, basically overloading the internet and causing some real life effects. 9/11 emergency call was not available in Seattle. Some airline tickets were not available. There are lots of damage that occurred through this activity. Basically, the servers in the internet, many servers in the internet were very busy processing this kind of effect instead of doing their regular tasks, and those services were not available. So there was the first message basically, and then the message caused the attacked servers to become attacker themselves, and basically by addressing one single server with that UDP packet, that single server was corrupted and was sending out UDP packets itself, and that caused an exponential growth of affected servers, basically requiring to bug fix as quickly as possible that issue in order to restore the service operation again. So what was the cause? So first of all, it affected MySQL Server 2000, and there was a service in this offered to search for databases on a network, and it was UDP based, specific port, and the first byte determined the request type, what you're looking for, search for database, and you had a maximum 10 bytes to specify the name, and this 10 bytes had to be null terminated. That means that somewhere in this 10 bytes there's a 0 byte which is followed a 04 byte basically. So this was the end that is showing that the message and the query is where the end of the query is. Okay, and then the SQL server takes this and assembles it with two other strings to a constant length, and you had 128 bytes in order to put this on the stack, and the server was basically receiving the request. So in the stack, basically the memory correlated to the process. There was written somehow request, there was the name, it went until there was a 0 and a 4, and then there was two other strings. And basically for all of these you had 128 bytes. So, and one issue that was happening here is it was not checked whether the UDP really contained only just 10 bytes. So what happens if the packet was larger? If you go back, then basically this name, that it's not checked whether it's at maximum 10 bytes, could be longer. And if it exceeds this 128 bytes, what happens then? Then it's continuing to write into the stack, and depending on where it writes to, maybe I should have written it more in that direction. So basically it reserves 128 bytes, and then it writes in that direction. And at one point it exceeds this part which was reserved for storing that information, and then it overwrites the other parts in the stack. And one part that it could overwrite is the program counter, or the return. Yeah, it's basically the return address. What's the return address? The return address is you have all heard communication architecture, so how CPU is working internally, how memories are maybe used, and basically how what a program is you have this lines of code, of machine code. These are maybe 32, maybe mostly 64-bit long, and basically they describe what instruction should be executed. This is just how a program internally in the CPU is processed. You have this line by line, basically, in which you process these commands, these instructions, machine code instructions, line by line. And if you jump to to a method, then basically there's some jump command and there's some address. And at that address, you find a new part of code with the lines. And basically, before starting and executing the commands, you note the address you jumped from. That's the return address. And then you have your code, and then you have maybe your allocated. Now, basically, first you have this allocated 128 bytes, and then you have your code. So the problem is, if you had this buffer that was reserved for the storage overwritten, then you could also overwrite the return address. And if you dedicatedly selected a specific new information that you put at this specific point in the storage, in the stack, then you can control at what point your code should continue. For example, where you also could continue with the execution, so basically it's very hardwired. So there's a pointer which current line should be processed next, and basically the CPU reads that line. It increments the counter so that it basically, after it processes this line, it processes the next line, and then once it read it and processes it, it processes the next line, and it's basically pointing to where the CPU is currently running the code. And what you could do is, for example, if you are able to return to modify this specific pointer where it should continue the execution once this method is done, you could, for example, also point it to the code that you provided yourself. Yeah, and 128 bytes might be sufficient to create some kind of code which uses this part to be sent around to other servers. And their stacks are then overflooded, and basically the return address is overwritten, and they act now themselves as spreaders of this malware. So let's have a look at this buffer overflow issue that was caused by a single packet. So basically the attack, if the UDP packet starts with the request, and when it's about to send the name that you are looking for, that's a discovery service, you also provide the meshing code of the worm. So basically the worm is, we'll see that later, it's basically some kind of virus that spreads over the internet. And there's no null byte, so it's basically not signaling that it's ending somewhere. So basically the whole worm is written into your stack. And if this is your stack, this is the return address. So basically once the packet is received, sorry, learned I have to pull this over, so then it's doable. So the return address, and then it reserved 128 bytes, 128, and here's basically the code that's to be executed. And what it does, it fills the UDP packet, fills the data up to a point where it also overwrites the return address, and the return address points then within the part of the code that you provided, that the attacker provided. And what is written inside here? It's written inside there that it basically first selects a random 32-bit number, because this can be interpreted as IP address. Then it sends itself to this IP address, and it's copying the memory area in which the running Slammer's instance is running to that machine. So basically it takes this, what was provided for itself, has it in that stack available, and sends it to this IP address. And basically then it at the last point it has a loop back to jump again to the point where it is starting the whole process again. So basically again selects a random 32-bit number and sends the message there, and basically that specific server now becomes itself a spreader of that worm. So, and why is this so effective? So basically, it's a very small part of code. So it is using UDP. That means you can just send a single message without any further effect. So in contrast to TCP, where you need a handshake, where you need to keep resources on your own machine available for it. So for TCP, that specific machine needs to memorize which open connections it has and so on. It needs to maintain the handshaking protocol. It has to know which messages to send, how to react on it. That requires more code. I mean, it's obviously you have various messages to exchange at the right time. So you need to keep state, and that takes more code than just to create a single UDP message and send it away. It's relatively small, so all the whole code fits into one message. And it's self-replicating. So basically, once you by random selected an IP address that was vulnerable to this attack, itself became a spreader of that node. And it was quite likely because let's say 32 bits are still a large number, but it's just 4 billion, so 4 million IP addresses. That's not too much. So if you give it some time, you still can create, I don't know, even if you create, 100 or let's say 10 packets of that kind per second, you still reach a large number over the time. And because there has been a homogeneous infrastructure, so the server has been in quite many products, quite well spread, with the same vulnerability, it was likely to find an IP address that was also vulnerable and affected and could be then used as an SQL slammer. So, quite impactful event. And basically we are looking now into this kind of malware, what kind of issues we can have and how to react to this. So we are looking into viruses, worms, trojans, and botnets, and have some examples, especially also viruses. There will be in the lab one exercise for this where you should write your own virus and get somehow to know how it internally works. So let's start with it. So what's a virus? That's a code fragment. This is the essential part. So just now we had some exam on network security from the last semester. So those who didn't write the first exam, and this was also one question: what's a virus? And the core elements are it replicates itself, and I think even for that I gave full points, but also it spreads beyond the boundaries of the single system. So it tries to not just a system, let's say also a file. So if it affected one file, it tries to affect other files, especially those on external hard disks, on USB disk, and wherever it can try to reach out of the specific single system. And then if it's sent around, if it's shared around with a USB disk, then this is how it spreads. And it executes without consent of the system owner, obviously. And in the times, let's say when physical copies were sent around, let's say of games or software, typically many of those were affected once by one single machine, and then it spread with the spreading of the software. Why are they interesting? Well, it's easy to do. You don't really invest your own resources. Obviously, you have to create the virus once, and then you have to spread it somehow, but then your task and your job's already done, and the victims themselves are participating in spreading the virus. And it's easy to spread, basically, because you don't really take influence on where it should spread. It's just, it can compromise many systems without specific target, and it just spreads. And then the question is, what additional functionality and feature does it contain? So obviously, part number one is that it replicates itself, it tries to spread, but there's also some kind of additional plus malicious code. So some activity, some other feature, some other functionality that it, in addition to the spreading mechanism, tries to achieve, such as installing some kind of keylogger and obtaining data and sending it somewhere, or I mean, or putting people under pressure, encrypting their files, and then asking for ransom. So there are various additional malicious options available. So what do we need? So let's say we are the evil guy now, and we want to build a virus. What are the questions that we need to address? So first of all, what vulnerabilities are there to exploit? I mean, obviously, the machines and the systems are not willing to be compromised and do not want to have those regular files modified in order to become a virus. So where are vulnerabilities and issues that could be misused? How can we spread it across system boundaries? How to program a virus, and how then from the good side, let's say still, so if there's detection options, what can we do as a virus developer to not be detected? Okay, so how is the current situation? So previously, lots of viruses were programmed in assembler, so really low code and low level programming, machine code, very close to the machine code level, where you really needed extra information and you really needed some knowledge and how the machines work, how this is how to really dedicatedly address problems in, let's say, the execution of machine code that you can misuse. So you needed to be educated. But now there are simple virus construction kits, from complete kits to special libraries where you really can click and point, and you customize your virus generation, and it's quite simple now. So also the virus development is professionalized, obviously illegally to make money. So one typical use case is that your files are encrypted, and then you are shown some kind of Bitcoin address where you should pay the ransom to in order to get your files unencrypted so that you can use it still. And therefore also there's really some kind of tool support, there's some kind of service provided in building viruses. So it becomes very easy. You don't need any more specialized knowledge. It became quite easy. So what can we do? How can we detect viruses? So the first step, how's the antivirus software working? Obviously, it first scans the files. Yeah, so you have executables. So regular text files or anything that is not taken as instruction is typically not affected. So text files or bitmaps, but it becomes a gray area when you have, for example, doc files with macros. And just now I'm also supervising one bachelor thesis who is looking into automatic malware detection in documents. What was very interesting demonstration he had is that you could have on your machine macros disabled, but still if you open a specific file, it was able to start the software on your machine. So for example, he started the calculator. I mean, just by opening the Word file, although the macros have been disabled. But because Word and let's say PowerPoint and Microsoft products and other software writing tools, not software writing, so writing and document editing tools support some kind of macros and some kind of additional features, there are some parts of this document that is shared is also taken as an input for executable additional software such as running macros. And then if you know how to construct the documents, then you can also enable it to run additional instructions that are not intended by the one who's running it. So what do the antivirus software do? Basically, it scans the file. So basically, it looks, what is a file? Again, it is a set of, if this is an executable, then you have a set of instructions, either machine code or it's read and let's for simplest part take this is exact machine code that is compatible to the CPU that you are using, as you know, for Windows or let's say for x68 processors such as Windows is running on. You have specific machine instructions that can be used. For ARM processors, it's different, so they are not compatible. For Mac, it's also a little bit different. So it depends on the processor. But basically, once you have this kind of machine code instructions line by line, typically if you call this program, then the first line is first executed, then the next one, and so on. So, and the antivirus software basically looks at all of these lines and tries now to identify patterns that, so antivirus software has typically a long list of patterns where it knows, okay, this is, I don't know, an SQL slammer. So this kind of code pattern only occurs in that specific virus, or some specific other pattern in this code is associated to another virus. So basically there's a database in the antivirus software that knows, so the company has analyzed the viruses that are out in the wild, has identified what are somehow identifiable patterns. It has put that information to the database, and then when it checks your file, then it can check basically whether it has some matches of the code in that specific file that relates and tells us that it's a specific virus. So this is step number one. Step number two is it can also put a sandbox around it. Yeah, so basically it is a safe environment, and then it runs the software, and then it checks for system calls and interrupts. And if there's some strange pattern, it can raise an alarm. So whether there's some file accesses. So for example, if the virus encrypts the whole hard disk file by file, and in order to later ask for a ransom to get some to get the files decrypted, it has a quite strong file access pattern. So every file is opened, every file is modified, every file is closed. So this is already strange. Or if it opens specific programs that are known to be potentially dangerous, if it opens communication ports, that can also be raising an alarm. So let's say if you have a text editor and you open the file and it wants to communicate to the internet, then it should be checked and confirmed by the user. So basically two options, either using for signatures in a database, or to look for behavior in some kind of sandbox environment. So how it interacts with the host environment. Okay, and basically it's a kind of cat and mouse game. So the development of viruses and of antivirus software depend on each other. So basically first, there's innovation in the virus department. They come up with new properties, with new options, with new activities. Then somehow the antivirus software producers get copies of these viruses because people are reporting to them that it's behaving strangely. So they have some examples from the real world. Then they analyze it. Then they find the signatures, or either again signature that they can put in their databases, or they have this behavior that is identifying the software, the virus, and that's also put in the database basically. So now at this point, the antivirus team is leading, and then again the attackers analyze the antivirus software. It looks what kind of signature did it take from our previous virus. How should we modify our virus now so that it's not anymore detected? And then they develop a virus B with modified signature so that it's not detected anymore, with slightly different behavior in interacting in the sandbox. So let's say you still want to encrypt the files, but because you know that the antivirus software is putting a limit, let's say if you open more than 5 files within a minute, I don't know, within 10 seconds, then this causes an alarm. So then you just open 4 files. And then it jumps basically back. The antivirus software still gets the copy of virus B, can analyze it, can adapt its detection rules. And therefore it's always also needed. So if you have antivirus software running, to update always, to periodically update that software to get a new database with the newest developments, to be able to detect then virus A and virus B. Okay, let's have a look at a very simple virus. I think this is also the one that you should then develop. So how is it typically a very simple one created? So let's look at those executables, so COM files. These are also executable in Windows, and it is very simply built. So first there's some kind of prefix which describes what it is. That's a executable. That's a file of that executable COM type. And then there are some data, let's say variable definitions. There are some, I don't know, strings that are needed in the files. Basically something that's not executable, typically variable definitions. And the first executable line is basically here at the address 100, and it jumps to the address 400. And basically here then you have the lines of code that are executed step by step. Sometimes, let's say if you have a print A, and A was defined here, then there's some resolving, I mean jumping back. So it will be resolved in print, I don't know, address 120. So pointing back to your variables that you defined. And yeah, then the executable is completed. So how would you place a virus in here that could infect other COM files? How would you modify this single file in order to make it? Where would you put the code that's self-replicating, that opens other files, that copies itself in it? So at some point you have to add the virus part, and at some point you have to make sure that the virus part is executed. Yeah, somewhere here, okay. But let's say, so where would you put it there? So for example, I mean, we don't know exactly what's happening here. So there are also many jumps. So it might be, if you just put it at the end, let's say we put it here. Okay, so let's in the executable part. Okay, so let's say if we put it somewhere in between, I mean, it should be so generic that you can copy that part of code everywhere, every kind of this COM file. If you just put it somewhere here, you might break the original function of the code. So I don't know, there might be some, if A larger B, then I don't know, jump to C. So it might be that, let's say, this part where you copied it in is never executed because A is never, let's say here C, and A is always larger than B. So this part would never be executed. This is also something that we don't want. Or if we put it here, then we could have here at the end some kind of loop, and this part is also never executed. So what other generic option would you have? Sorry? First one? First line. Yeah, if you put it here, it's first line, then it's not anymore identified as COM file because you need this prefix first. Hmm? Okay, so this is the first line of execute, jump 400, so it jumps here. So that would be a good option to modify. So what you could do is, okay, I have to jump into my virus part. So let's copy it at the end. You will always be able to copy the code to the end. You don't break anything with that. So you copy your code up here. It's easy to just append to the file. You say you modify this single first entry. It should jump to your code. And then the last line you have jump to the regular code. So that first your virus is executed, and then the regular program is run. So how could you detect this? Do you see a pattern that could be recognized as potentially malicious? Yeah.
You look for device address that could be possible, and see if it has a higher address in the jump.
That's right. So you could say, okay, this is the, let's say, first regular element where it should jump to, and maybe in COM files it's also somehow specified that it should always jump to line 400. And if it's something else, then it could be potentially malicious. Also, what you could see is that, yeah, if the jump goes somewhere else than after the data, not executable parts, then that could be also considered as potential threat. So you could come up with some kind of rules, or I don't know if you always end with a jump back to the very beginning of the regularly executable part. That's also might be suspicious. I mean, obviously you can also have regular files that start here and have at the end a loop. So then your signature, your pattern that you would identify would be also causing them to be identified, although they are probably not malicious. But maybe in combination with jumping first at the very high point. So maybe it would be okay if you jump to 400 and at the end you jump also to 400. So that would be fine for a regular one. But if you jump somewhere else than 400, so not 400, and at the end you jump back, that could be a pattern. I mean, it's a very simple setup. So in these kind of signatures, these are the patterns that basically the people at these antivirus companies, they look into the files, they try to generalize it, that are basically what they try to achieve is to have as many correct matches so that only viruses are found, and as small as possible false positives, where basically you identify a regular file as a virus that is no virus. And obviously they want to also minimize the false negatives where you overlook valid viruses. So basically these signatures are these characteristics of a virus. These can be, as we had it in this case, with jumps to strange positions, but it can be also a pattern of, let's say, if you have 5 specific commands one after another that mostly occur in viruses, that you could also say this is a signature that we would increase the probability that this is a virus. So very simple, distinctive sequence of bytes, and it is very simple. So let's open the other file that we had with regard to snort. And with regard to snort, let's see, snort, did we have it here? So this was the example we had. So snort was the intrusion detection system for networks. Yeah, basically it looks into the file and then it says, okay, this is a specific pattern of bytes in the message that is considered malicious, and therefore I raise a flag, I raise an alarm. And we have seen this various examples how this is defined. Basically, if you have specific kind of patterns in traffic, in messages, if you see this pattern, then this is associated to this kind of malware. If there is this specific string identified in the message, then this is a potential malware element. If this is, so basically you have, these are the signatures that we had in intrusion detection systems, and intrusion detection systems are like antivirus software for network traffic. So also the regular antivirus software is following this kind of pattern. So it looks for the signatures, and based on its large database that have been accumulated over the years, and it tries to basically identify them. So often very generic signatures, describing characteristics of whole classes of viruses using wildcards, allow mismatches, and so on. Basically, they are focusing on important parts of the files at the very beginning. So if we focus at the first jumps, then we could, for example, identify the modification that we had in the previous example, or at the very end. Also here, I mean, the virus was here at the end, and the first jump was the relevant parts. So let's say you know now that the antivirus software is looking at the first jump and at the end of the files. What would you do in order to be not so easily detected? Yeah. So let's say the focus of the antivirus software is on the first jump and end of file. What would you change in your virus setup? To jump back, yeah, maybe, yeah. Let's see which jump back. So let's scope it out a little bit more in broad. So if the first jump is analyzed by the antivirus software in detail, maybe the other jumps are not so closely watched. So what you could do is entry point obfuscation. So previously, as we had it, here's the prefix, then there's the jump to the end, and that was basically showing that this is a virus. But let's say we are just regularly, here's the prefix, then we have the data, we jump as in a regular file, we jump into the code of the regular comp file, here are some instructions, and here's another jump, I mean, just like the comparison, if A larger than B, then go to C, and C is here. What you could do is to take the first jump or the fifth jump or the 17th jump and jump to your code of your virus. And once your virus finishes, then you jump to C, so the regular one. So basically you just introduce, it doesn't jump to C directly, but it jumps to virus and then it goes to C. So you just pick a random jump place in the code that anyway is in many code available, and you add this a little addition that first your virus should be executed. So then it's more difficult to analyze because you could say you don't take anymore the first jump, you take maybe 17th jump. So then the antivirus software has to basically analyze every jump, whether it's a regular one or not. And then it becomes more difficult to identify, is it really a regular jump or not? So you analyze your code to be infected, replace the jump function with the jump to the virus, and then after the virus finished, you jump back to the regular place where it should be executed. So this is entry point obfuscation. So the antivirus software now needs to scan more code for virus infection. So you made it more expensive for the antivirus software to identify your virus. Okay, so what should the good guys do now? Okay, so this was, let's say, the first element where we identified based on the jump. We're coming back, so that was what what the virus producers could improve. End of file, but also what they also are looking for, the antivirus software, are the signatures. As we had the example, specific patterns of this executable lines. So if you see, for example, 5 specific instructions followed by each other, I don't know, open a file, copy one specific part of this current file into the new file, and then close it and modify maybe 1-2 lines of code in the new file, that might be very suspicious. So because it's quite rarely that you really want to copy one part of a file into another file and modify jump instructions there. So if the virus is made of these single lines, and we are identifying either specific patterns here, I don't know, 5F, E7, so as machine code instruction, or the lines themselves are problematic. They can be analyzed, they can be detected, that can be identified as a signature, and the virus is detected. So if the virus producer know that this constant sequence of bytes are easily to be detected, what can you do? How could you hide in the file your lines of code? How can you hide information? Mhm.
So for this data that we use as code, but for the program it just looks like there's just some data there.
Yeah, that's good. So let's again have this example. Here we have the code, prefix, you have the jump. Here we have data. And here we have some code, the regular code. So what you could do, that's right. If, let's see, this is your lines of code where you put it in, it should look like regular data. But let's say here you have a very small part of code that allows to read this kind of data and identify it as potential executables and instructions that should be executed. So this is a very small part of code, but this can be very long and contain all these malicious patterns. How can you enable that you can see and read the instructions correctly, but the antivirus software cannot? What kind of mechanism do you typically have to hide information from others? Provide confidentiality, actually. Encryption, that's good. So what you could do is to encrypt viruses. So what you do is you have two parts, decryptor and the main part. Basically, in the example before, you had a very small code, that's a decryptor. Decrypt. You had the data part, which can be quite long, and this is all encrypted. So if the antivirus scanner looks at it, it's just random data. There are no patterns. It's encrypted. So it cannot identify any kind of malicious instructions because it's encrypted. And then once the code reaches your decryptor, you can basically decrypt it during the runtime, copy it somewhere, and execute it. So what we changed now is previously the antivirus software was just able to look at the code without running it, identify the signatures, and then identify, this is malicious, it contains this specific signature. But now if it looks at the code, it just sees garbage and encrypted data and doesn't, encrypted data always looks like random data. It cannot be interpreted. So, and only once if the decryptor is executed, then it unfolds the whole magic and the whole decryption takes place and the malicious instructions are visible and then they are executed. So during the runtime, the decryptor decrypts it and then executes the part. So, and the execution, even to make it worse, if the virus A, wants to spread to another file B, it can also add a little bit of, it unfolds the executable, the hidden information, and it re-encrypts it for the new file. So the new file B has now different kind of random data that is not visible, that it's not interpretable by the antivirus software, and that data part looks different than in file A. So every new file has now a new kind of string pattern in the data part that is then later decrypted by the decryptor and then executed. For example, what you can do is you just XOR it with some kind of constant, and the constant, you write the constant here. This is some random bits, but once you apply it to that encrypted data, XORed one by one, you get the executable lines of code. And this constant can change from file to file. So you simply XOR in a loop over the code, and then you run it. You can also, yeah, when spreading to other files, choose a new random value. So every virus file looks now different. What can the defender do? So the malicious parts all look different. No signatures to identify. But what could you still identify in all of these various files A, B, C, D that are generated with different random looking data at the front? Sorry? Yeah, I mean the problem is you suggest that the antivirus software should have an decryptor? Yeah, that's right. Very good. Exactly. So what they all have in common is this decryptor part. So you could identify, so encrypted code is hard to analyze, but you can detect the decryptor. So basically, you can, if you analyze it, and you can try to identify which parts in the code are using as an input some data that it had. It processes over a bunch of those lines, and those lines are later then executed. And this specific behavior you could identify as malicious and basically raise a flag. Step number one, so basically this is the static analysis, so where you just look at the code and you see there's the pattern for the decryptor. So you have a signature for the decryptor. But you can also have it dynamic. Dynamic code analysis means you run the code and then you learn from its behavior and interacting with the environment whether it's potentially malicious or not. And specifically, when you see that there's the code not trying to take from the data part the lines, it processes it, it writes it somewhere else, and this is now then executed. This behavior is then considered malicious. Basically, if you take code from the data part, which is later then executed after some processing. So, against the statical element, maybe we will have something that we are able to do. But let's first look at this part. So if there's a debugger running and you know the code, the virus will be in a dynamic code analysis environment, so debugging and looking for patterns and how the code interacts with the environment. How could you prevent being detected? So let's say you know that the antivirus software checks whether some part of code that might be a decryptor takes data, processes it, transfers it into some new region of code and executes it. If you know this will be marked as malicious. Yeah, what could you do? Now there's the element of theoretical computer science popping up. So there's this term Entscheidbarkeitsproblem. So the how's it? I think that's also the general term, but the English one, decision problem or decidability problem. Do you know that? What does that mean? So the question is, I think Gödel brought it up. So if you observe a software, you are unable to determine whether it will end at some point. So the question is, if you're an antivirus software producer, how long will you observe the software? until you come to a conclusion. The virus producers know that it will not happen for an unlimited amount of time. So they know that, let's say, the antivirus software will take a specific amount of time, X, in which they are closely looking at the code, and then they will give up. And then they come to a conclusion and basically consider it's safe or not safe to run. So what can you do now? Any ideas? Yeah, so you could also have internal timers that you only become active once a specific time has been reached. So that for, let's say, there's so let's say only after 1 hour the malicious code is activated. That's then more difficult to observe. But another point that you can do is to make use of the knowledge that there's a breakpoint. Basically, the antivirus software tries to stop the execution also in the sandbox environment and tries to trace basically what is internally happening, tries to stop the execution at one part so that it can be processed, whether it's malicious or not. And basically the question is, can you as an attacker identify whether you are examined in the debugger or not? Can you identify that you are running in an unsupervised state or whether you are running in a sandbox? And basically what you can do is to use some interrupts. That means, what does it mean? I mean, now we are going a little bit more into how code is executed on CPUs. So basically, if this is the line of code, how you go step by step, there are some higher prioritized events that can cause an interrupt. So basically, that the execution is stopped at this point, and some other code is executed, such as for the debugger that looks into what has happened to inform the debugger, and then once it's informed, it's processed back, and the next steps are done. Basically, some interrupts, these higher level, root level code breaks, basically where the code execution is stopped and some other things are done, such as the debugger, and then jump back. You can basically check whether they are in use. And some viruses override that ability to stop it, and either that they disable the debugging so that it's if it's called basically to jump back to jump out so that you can execute the debugger and then you to jump back, you could override it that these jumps don't happen, or you could also, if um, basically modify that not the debugger is called in case that a debugging event occurs, but your decryptor should be launched and the virus should be activated. So it's basically going into a meta level of viruses where they do not just try to execute their malicious task, but they try to identify whether they're in a sandbox and use the executions that are linked to that sandbox to cause more harm themselves. Okay. How can this be done? So now that's very low level, deep level, and this will not come into the exam, obviously. But one example how this can be checked is if you so if you want to detect whether the debugger is running and whether there's some trace information stored on the stack. So every executable has this additional memory, it's operational memory, the stack that the process can use. And basically what you can do is, so how it's done, there's some kind of info on the stack which tells what is executed next, and then it jumps back and the info is updated so that the debugger can keep track on which line are we, so that you can go step by step through it. So basically the debugger controls this left part. so that you can also interrupt the execution line by line, can make dedicated jumps in the debugging. So the debugger decides when to do the next line in the list of instructions. So, and basically, if the execution itself tries to write something there and then take it back, then it can identify, oh, this information has changed, although I myself did not change it. Somebody else changed this information that I'm trying to use. So basically, the executable can try to read this information and compare between the various instructions whether this information has changed. And if this information has changed, then I'm in a debugging environment. In a regular environment, when I have these lines of code and I write something here in the information space and I read it later, it should be still the same. But if I'm debugged, then this information is modified by somebody else that is controlling my execution, so there's a debugger running. So that's happening here. So it uses, basically it stores a marker on the stack. In the next execution, it loads the marker from the stack. It tries to compare the two values. And if they are not matching, then we learn that the information has been modified by somebody else. And if it has been modified by somebody else, then we jump to an execution element where we are very nice and do nothing wrong, so that we know we are under supervision, so therefore we behave well. Okay, so this is with regard to the dynamic detection, so that the viruses can detect whether they are observed or not. But coming to, where did we have it? Okay, so that was step number one, to identify that we are, yes, that was it. So that was the dynamic checking. We are able to identify whether we are observed. Let's see whether we can modify the decryptor. So if the decryptor has a specific signature that's easy to detect, what can we do to modify the decryptor so that it's not anymore easy to detect? So how can we change the decryptor, how it looks like? So first of all, what we can have is to have oligomorphic viruses. That means we don't have one single decryptor, we have many. And every generation uses one randomly. So that if we have a file A using decryptor, I don't know, A, it has a set of other decryptors which are also encrypted in the code. And once the code is opened, it selects from this large set of decryptors another one. And if it infects file B, it uses a different decryptor so that they are not related anymore. They both contain this encrypted element in the data part, but that looks like random. The decryptor changes from file to file. So the more decryptors you introduce, the higher the chance that maybe one decryptor is not known to the antivirus software. Looks a little bit limited. So let's say you have here 23 options. You might be limited at one time. You always have to manually introduce new versions. Let's make it more dynamic. So let's use polymorphic viruses. That the decryptor itself is not limited to 23 versions, but the decryptor itself changes with each generation. So what you can do is, if you have a specific instruction, such as you want to calculate a plus b and write it into the memory area of C, you could also do, you can replace it by a minus b and write it to C. Or you could replace it to A, write it to C, and a C equals C plus B or so. So you can, for every instruction that you have alternative implementations. And let's say you have instruction A, B, and C. Then the next time you have maybe small a and big B and I don't know, C. And then the next time there's A1, A2, and then there's small b. So you have always wild combinations how your code looks like, because you are replacing parts of the code with equally resulting results, I mean with equal instructions that look different. So you could, for example, this is so this means okay, yeah, let's say if you want to say C equals A, then you can also say that's or A, or that it can be 0 plus A, that can be anything else. So you have equal instructions that you can replace. You can also insert meaningless operations in between. I mean, if you want to still compute A equals E plus B and the result should be stored in C, you could also calculate D equals A and E equals B, and D plus E should be written in E, and then at A plus B, something like this. And all of this was irrelevant. Okay, also if you know that, let's say the antivirus software is looking for a decryptor of, I don't know, 5 instructions in a specific pattern, that it opens the text file, it processes the data, it writes it somewhere else, then you can first open the text file or the text area and read it and write it somewhere in the storage so that you just have it. Then you jump somewhere else, you do something regular, then you jump back, and then you have the decryption. And then again, you jump somewhere else to do something else, and then you jump back for the execution. So if you split your own potentially identifiable code into smaller snippets that you distribute all over the code, it's not anymore at one single location, and it's more difficult to identify as being connected. Okay, so this is getting even more difficult. And you can also get rid of the crypto itself and change the virus completely. We have so-called metamorphic viruses, where the main idea is you have here the code. See, is it? Yeah, okay, you have the code. And the code has the regular virus elements. So it has here the links. These are all the malicious executables. What you want to do is that every copy of it, every replication looks different. So from this single code, we want to have here this line of code, so it should be different, and in the next file it should be even more different, so that no single execution file, no single virus looks alike. Because the signatures can only be created if you have various copies of the same virus to see what's the common part that you identify as a element that can be detected later. So how can you do this? So what you can do is so it has its own source code. It's disassembles itself, so that means this meshing code is recreated into the operations. I don't know. Then let's say we have also D plus E equals F. So you can, for example, scramble the code for changing the function. So you can change the order because F and C are not taking effect on each other. So you can change the order. You can you can introduce additional new lines. I don't know, 7 plus 2 should be written in C before, and then C is overwritten. You can again you can replace, as we saw it before, the operations by equal operations but looking different. So basically there's a rule set of how your source code should be modified before transferring it to another file, so that the next file looks different and the next file looks different. They are all doing the same, but the code looks different. Also, if you do it well, you can adapt to different operating systems. You can take into account environmental options. If you're on a specific CPU, you could try to leverage on dedicated instructions that only that CPU offers. So you can really optimize your code also to be running on specific CPUs. which are then even more difficult to generalize for the antivirus software. So this is quite difficult. So what can we do now? So if the code itself is difficult to analyze, so if we have the scenario and every code looks different, there are no really generic parts that they have in common to identify them. So the static analysis is difficult to achieve. So static analysis, again, looking at the code without running it and trying to see the generic patterns that can be identified as malicious. So what can we do?
Check for suspicious access.
That's right. So we need to run it dynamic. We need to run the code and to see what's doing. Because although the code looks different, it should still behave the same way. And from this behavior, we could probably identify malicious intent and malicious tasks. So we need, we run parts of the file we want to examine. If the virus is present, it must show up at some point, yeah. Obviously not in a normal system, so we need this kind of sandbox environment again. We need to emulate the code, basically trying to identify what it's doing, trying to also have this debugging functionality that we also talked about, and then to try to learn from behavior. And even, let's say, even if we have this kind of sandbox environment and we don't have the debugging, so debugging is a little bit different than from sandboxing, because debugging is looking at line for line what it's doing and it's trying to keep track of it. But the sandbox, there the virus can do whatever it wants, but it cannot access real files and cannot access real resources of the machine. So there's some kind of boundary, and it will not learn that it's trapped. So it's a little bit different than debugging, which enables it to really learn that it's in a debug mode. Okay. So, and what can then be done? The next step. So basically, we first let it run regularly. So execute the decryptor at some point, and then we try to monitor basically the storage, the stack and the memory of the process. So if these are the instructions and it is using some kind of stack somewhere to store information and it has some kind of information in the memory, we also observe this and we observe the memory, whether at some point in time we have some kind of patterns that are considered malicious. So once the decryptor decrypts the data, it will be in plain text somewhere in the memory. And if you look also into the memory, not just in the code, then we will be able to identify signatures. Yeah, the problem, I mean the memory might be quite large. And also, how long do we wait? Again, we had this example that we are starting at time t0, and the code has the rule after specific time it should start with the malicious behavior. So this is an issue. And also, where do we start looking? Because if you consider memory usage of code can be quite large, and can also, if you consider, I don't know, if some networking is involved, every message that you create to be sent out is stored somewhere in the memory and could be read as instruction. So it's really difficult of which parts of the memory to observe and how long and I mean, that's really large data volumes. And if every time you try to interrupt and try to identify is it malicious or not, then you're also slowing down the process quite significantly. Okay, but still, it's a good approach to have the sandbox environment where when you watch it, how it interacts in the sandbox, what kind of resources it tries to access, what kind of communication it tries to do, what kind of so basically control the environment and try to identify malicious activities. So this characteristic behavior is then looked at. So for example, how many files are opened within a time frame, how many modifications to files are executed. But again, so it's always a cat and mouse game. So if and the problem of the antivirus software producers is that they code and their patterns, their signatures are basically available to the public and especially to the virus creators. So if you once introduce the code, the pattern, there should be no more than 5 files opened per second. They will adapt to 4 files per second. If you introduce the behavior of 4 files per second or reduce it to 1 file per second, then regular programs will break. I don't know, if you open a game and it wants to load the textures in order to present you the visuals, then probably it opens more files than 1 per second. Okay, so coming back to the problem, where do we have it? This one. So if it's difficult to have this kind of code of metamorphic viruses to be identified because every virus looks different. It's doing the same, so dynamic analysis is difficult, and the files look different. So what we could do is to take this red, green, and blue file and optimize the code. That means if we optimize the red code, it will be looking like this. If we optimize the green code and we have the blue code, once you throw out all unnecessary operations that have been introduced being not really needed, and if we let's say reconvert all unnecessary operations. So if we know that, let's say, a plus b equal, so this is where it should be stored, and this is the same as if we have c plus a and c plus b, and we have the same like I don't know. Let's make it 1 c times b and c equals c plus a. So if we would all convert this to the most basic operation, let's say they would be all converted to this, so we could try to recreate a very basic simple function out of differently looking files, so to come to some kind of optimized code. And then we see, okay, if we optimize green, blue, and red, we come up with the same optimized code, and this can be detected. Yeah, depends on the quality of the optimization, how well you can do this, how many alternative approaches you can identify. But it's a way to address this variety of code types that do the same thing. Yeah, it's quite challenging. So and by this code emulation, so for example, if we basically have the sandbox environment and the code optimization, that again, if it's known to the attacker, to the virus creators, they again can adapt to it. As one example we talked about is if we could detect that we are in a sandbox, we behave differently, or we wait for a very long time. Or code optimization could be also an issue, which could be, if it's known how the process works, you could find loopholes. And this is only about new viruses eventually. So, sorry, about known viruses. So all the signatures are only applying to known viruses. So what do we know about unknown viruses? What should we do? So basically what you have is you have a signature for virus A, you have a signature for virus B, you have a signature for virus C. And what you want to try is to generalize. So what is the common pattern that they use? And this is where heuristics come into play, where you can identify new viruses by somehow abstracting what is typical virus behavior. So, for example, to fragment searches for certain executables in certain directories. So, if you know that viruses typically address, I don't know, system, is it still a thing? Is it still system 32 folder? I don't know. So where somehow Windows executables are, and it tries to open many files there, or to search in files in specific regions there, then that's already strange. Or if the code itself modifies itself at the runtime. So what you expect by regular code is you jump somewhere and then you execute it. What you don't expect is that you jump somewhere, it tries to read the data, it tries to write it into some stack and execute that. That is typically not regular behavior. So anything that goes beyond executing what is already in the file, and it's about executing something that was put previously into the memory, is suspicious. So you could accumulate this kind of suspicious activities. So it might be that, yeah, this is 20% suspicious. But combined with this is 70% suspicious. So you accumulate maliciousness points. And after a certain number of points, the program is considered as infected and malicious. I mean, this is a heuristic. So if every malicious activity or strange behavior adds points, and this is transparent and basically also communicates to virus creators, they could try to minimize their points, but also you don't have guarantees. Also harmless programs can accumulate those points. So it's just heuristics. So how could virus programmers react to it? So if you know you can accumulate points and then can be considered as malicious. So what you could do is obviously to accumulate less points. So to act slower, to have regular behavior, and just in very few cases there's some kind of strange behavior. So here's an example, Win32 simile. So what it does, it first searches for executables of the PE files, these are executables under Windows, and it ignores a number of files that are considered as traps by antivirus vendors. So probably there are also some files located in the Windows executable folder, which have been put by antivirus vendors there. And once they are modified, they check which process is modifying this file. It should be never activated, just some honeypot, some trap. And then the antivirus software knows, okay, this should be considered malicious. So, and the remaining file will only be infected for a small, 50% probability. It can be also smaller, so that it behaves slower and it doesn't affect with 100%, but it has also some regular behavior that could lead to that virus is not detected as malicious because it didn't cause harm. So, and let's say it once has been, let's say if we reduce this to 10%, and then 9 out of 10 times it has been considered as normal file. If there's one outlier, probably the antivirus software has some kind of internal history mapping to that file, and then it knows, okay, this is one strange behavior, but in 9 out of 10 cases, it was working correctly. Okay, what it also does is it replaces certain function calls from imported DLLs. So by calls to the decryptor of the virus. So the file specifically typically also calls DLLs, so some kind of libraries under Windows. And what it does, it modifies it to jump to the decryptor. And after decrypting, it jumps to DLL and continues. It can also be in different parts of the code, so code, data part, program part. So if it's different locations that need to be looked at the same time. And this is the last slide for the viruses. After that, they will talk about worms, but not today. But just to complete it, what it also had, metamorphism. So it first disassembles itself to come to the higher level programming language, so that it basically has a higher level programming and not anymore meshing code that is easier to detect. It can adapt to various operating systems. That's a step. It is optimized and minimized. So the original code. So first we come from big code. That's the virus. Then it's minimized to its core. Then these core elements are split into single blocks, and then they are distributed at the file. And each individual block is implemented by different methods. Again, you can implement the addition by different means. So the single blocks are replaced by other options. Then there is added redundancy and code fragments, and then it's assembled back and copied to the new file. So it's basically a big file here. It's reduced to its core. Then elements are replaced, and then it's spread out again to be a big file. So that looks differently than its origin. And in 1 out of 4 cases, it does nothing, just executes a regular program, and the malicious code only occurs at a certain date. And if it's not that specific date, you are not detecting that it's a virus. So quite difficult to detect. But if you're looking to get a job in an antivirus environment, so there's lots of open new challenges that can be addressed. And that's a job that never ceases to exist. There will be always these dangers. Okay, so next time, prompts. And I think in the next lab, one of the examples will also be to program one virus and get accustomed to it, to know how to defend against it. Okay, thanks for your time. See you then, I think next week, because this week, on Thursday, there's public holiday, so we will not have any lab, but next week, see you then there. Have a nice